In this video, we are going to be talking about our last type of problem that is related to the simplex method, and this one's called dual method. And the idea of dual is, well, in the previous sections we learned about standard simplex and general simplex, and the requirements for standard simplex were the most restrictive. They had the three requirements. One, your variables had to all be greater than or equal to 0. The second one was your constraints had to be less than or equal to a positive number. And the third one was that it had to be a maximization problem. Well, dual method is for when everything is backward from standard simplex. Okay, when everything is wrong. Um, and the idea here was we could technically do um, any problem using simplex. Uh, I can't write and talk. There we go. Standard simplex. It, you could technically do anything using general simplex, but the process in general simplex became very it was much more difficult. There were a lot of extra steps. We had to star the rows. You had to flip if it was a minimization. Where dual method says, look, if everything is backward from simplex, um, this will be quicker. This will be easier. The steps are slightly different, but they're easy steps. So let's walk through the idea here. Dual methods requirements are the exact opposite of standard simplex, except for it still holds the requirement that all your variables must be greater than or equal to 0. You still have to have that, so we still can't have negative answers. Okay, but instead of asking for a maximum, it wants a minimum. And instead of all of your constraints being less than or equal to, they should all be greater than or equal to. Okay, so now the steps for simplex is going to use something we learned in matrices way long time ago, and I said it's going to go away, and then it's going to come back at the last moment, and here it is. Okay, so the very first thing we're going to do is we're going to write your system of equations as a matrix, but notice there's no mention of slack variables, there's no mention of anything like that. It's not the same kind of setup. All we're going to do is literally throw in a matrix, and then we are going to transpose our matrix. So if you remember what transpose means, your rows become columns, your columns become rows. Um, and so then you're going to rewrite your equations. And when I say with new slack variables, you watch what I mean when I do the problem. We're not actually going to be adding in slack variables at this moment in time, but we're going to have to just make up new variables because after we transpose, all of our columns and rows are going to get all mixed up. Then we're going to use, after that, so after you rewrite your equations, then you're just going to use the standard simplex method. So here we go. Oh, and then last but not least, the last caveat, a lot of students miss this. Your answer is read differently by the very end. There's a very special method to reading your answer when you're using um, this method. So let's do one. So what does it look like? What does it look like? Notice, okay, instead of maximization, we have a minimize. Okay, then instead of um, less than or equal to, they're all greater than equal to, greater than equal to, greater than equal to. Okay, now when we're doing this problem, um, step one, I'm not going to do the entire problem in this video. I'm going to start you off uh, with just the setup. Just the setup. Um, so here we go. The setup, what does it look like? When I said you write your system of equations as a matrix, what I literally mean is you just write them in. You go 1, 2, 6, 1, 1, 4, 2, 1, 5. Notice? Okay, there, I'm not doing anything. I'm just literally copying down. It's almost like an augmented matrix where you're going to do reduced echelon form or something like that. Okay, now for the objective, it still goes at the bottom, and we're going to fill it in. And here's the last little trick: the equal to, the constant, is always 0, always 0. All right, now here's the next fun part. If you think about it this way, x, y, and then equal sign, right? When I transpose my matrix, means my rows become my columns and my columns become my rows. So 1, 2, 6 was my first row, so now it is my first column. My next column will be 1, 1, 4, 2, 1, 5, 1, 1, 0. Okay, now here's the next fun part. Our variables have all changed because instead of x and y being up here talking about these columns, notice I have 3 columns now. So x and y is now talking about my rows. So I need to make up slack variables for my columns. So, and you can use any variable, any slack variable you want. So I'll use QRT. All right, now that was step 1. Step 1 was write it in a matrix. Step 2 was transpose it. Step 3 is rewrite your equations using your slack variables. So notice my first equation would be read, my quote unquote x equation would be written out as q plus r plus 2t is 1. And now here's the neat part. Here's what the transpose does is it makes every single equation, instead of being greater than or equal to, it is now less than or equal to. So the next equation would be 2q plus r plus t is less than or equal to 1. And then this last one is still my objective. My objective, just like always, would be 6q plus 4r plus 5t. Just like always, it's always equal to. But now, instead of being a minimization, the dual method changes everything to the opposite. So everything that used to be greater than or equal to is now less than or equal to. And if this used to be a minimize, it is now a maximize. And so it gets a p. So now, if you look at this problem, it's basically a standard simplex problem, is it not? We have a maximization, and we have less than or equal to's. So what we're going to do now is do the problem just like a standard simplex problem. The only thing that I want to finish up on this video about the standard simplex setup is what would our slack variables be? All right, well, so let the standard setup, let's get our objective, how it's supposed to look. So what we're going to do to our objective function is we're going to say, okay, p has to have a positive leading coefficient. Everything else has to get negative, so it's negative 6q minus 4r minus 5t plus p equals 0, right? Okay, there's our setup. Now, for the other equations for our constraints, what would these look like? Well, this one here would be just like normal, q plus r plus 2t equals 1. And our slack variable, since this stuff on the left-hand side is less than or equal to, we need to add to make it bigger. But now, what slack variable do we use? And we have to get our original variables back into these equations somehow. If we're going to get an answer, we need x and y in here. So the slack variable for the first equation is x, because that was the equation from that was the equation that x was this was coming from. So x gets reintroduced there. Now for the other equation, we're going to have 2q plus r plus t equals 1. And since this is all less than or equal to, we have to add to make it equal to. And its slack variable will be y. So now our setup for our problem looks just like normal. We're going to have q, r. Let me do this in a different color. We're going to have q, r, t, x, y, p, equal sign. And now we fill in, okay, the first equation in the matrix would be 1, 1, 2, 1, 0, 0, 1. The second one would be 2, 1, 1, 0, 1, 0, 1. And then our objective equation would be negative 6, negative 4, negative 5, 0, 0, 1, 0. All right. There we are. Now you do the problem just like normal. Just do this like a standard simplex. This is a 6, not a q. 6. There we go. So do the problem just like normal. And just don't read your answer. Now I'm going to go through it in the next video. I'll finish this up and show you how to read the answer. But if you want to do this on your own, just do it like a regular simplex problem, standard simplex problem, and just don't read your answer. Okay, we'll see you in the next video.